Have you ever really stopped to consider what it takes to just, well, read a sentence?
I mean, the sheer processing power involved.
Exactly. Not the philosophical side of it. I mean, the raw mechanical act. You look at a string of symbols and your brain just instantly knows that's a noun, that's a verb.
It feels instantaneous to us, almost like magic.
It is magic.
Hmm.
But if you ask a computer to do that, to look at text and figure out the grammatical role of every single word, you're handing it just a massive mathematical challenge, especially for a language like Arabic.
Oh, absolutely. It's one of those classic hard problems in computer science. We just take it for granted, but teaching a machine to see the difference between a noun and a verb when it doesn't know what those things are, that's a huge hurdle.
And that is exactly our mission for today. We are doing a deep dive into this fascinating paper. It's titled An Efficient Part of Speech Tagger for Arabic by Selçuk Kupru. And I picked this one because, honestly, the whole premise is just so audacious.
It really is. It kind of challenges the conventional wisdom of how you'd normally build these systems.
Right. So the researcher wants to build a system that can understand Arabic grammar with over 95% accuracy. But here's the catch, and this is the part that just blew my mind. He wants to do it without a dictionary.
Mm-hmm.
No rule book, no huge database of definitions, just raw math.
It's a bold move. It really represents a shift away from, teaching the computer the rules of grammar and moving toward letting it, well, essentially guess the structure based on probability.
Which sounds like a recipe for total disaster.
I
I
mean,
mean, if I tried to speak a language by just guessing probabilities, I'd probably end up ordering a shoe instead of a sandwich.
it seems counterintuitive for sure.
So before we get into the how, let's just set the stakes a bit. We're talking about part of speech tagging or POS tagging. Why does this even matter?
Because it's the bedrock. It's the foundation for everything else in natural language processing, or NLP.
Like what?
Think about machine translation, Google Translate,
Mm.
or information retrieval, just searching the web. To do any of that, the computer first has to know what role a word is playing in a sentence.
Can you give me a concrete example of where it all goes wrong if the tagging fails?
Sure. Take the English word fly. If I say, the fly sat on the wall, fly is a noun, an insect.
Right.
But if I say, time flies like an arrow, well, now flies is a verb. If a translation system gets that tag wrong, the output is just garbage. It might translate it as time insects like an arrow, which is, complete nonsense.
Got it. So the computer needs that tag noun, verb, adjective to unlock the meaning. But this paper is all about Arabic, and it makes a big deal about it being morphologically rich. What does that actually mean?
It means Arabic is incredibly dense. It packs a huge amount of information into a single word.
Okay.
In English, we separate concepts. We say the, and then book, 2 words, or I will write, 3 words.
We like our personal space, even in our grammar.
We do. But Arabic fuses these things. A single word can contain the preposition, the article, the noun itself, possessive pronouns, all just glued together. Gender, number, person, definiteness, it's all in there.
So for a computer, looking at an Arabic word isn't like looking at a single Lego brick. It's like looking at a whole pre-built castle that it has to somehow take apart.
Precisely. And that's a huge computational problem. A dictionary for English is big, sure, but it's manageable. A dictionary that has to account for every possible combination of prefixes and suffixes and roots in Arabic. You're talking millions upon millions of entries. It gets unwieldy fast.
Which brings us to the old way of doing this. The paper talks about systems by Habash and Rambo. They used what are called morphological analyzers.
Right, and analyzer is a polite word for heavy machinery.
So this is the brute force method.
Essentially, yeah. A morphological analyzer is a massive, complex digital rulebook. The computer sees a word, it checks this huge database for every possible thing that word could be, and then uses a strict set of linguistic rules to try and filter out the wrong answers.
So it's like carrying around the entire Oxford English dictionary plus a grammar textbook for every single word you hear.
And it works. It's accurate. But it is heavy. It's slow. And importantly, it's expensive to maintain. Language is always changing, right? New words pop up. If your whole system depends on a hand-coded dictionary, you're constantly playing catch-up.
And this is where Kopru, our author, steps in and basically says, let's just throw out the dictionary. He proposes a stochastic approach.
A data-driven approach, yeah. Using a hidden Markov model, or HMM.
Okay, let's pause on that. Hidden Markov model. It sounds like something out of a spy novel. What is the computer actually doing here? If it has no dictionary, no definitions, how does it know anything?
Imagine the computer is walking through a sentence, but it's blindfolded. It can't see the meaning of cat. It can only feel the rhythm, the sequence. The HMM works by calculating the probability of a sequence of tags. It's trying to find the single best path through the sentence.
The best path, meaning the sequence of tags, noun, verb, adjective, that makes the most sense statistically.
Exactly. And to do that, it calculates two very specific probabilities for every single word.
Okay, what's the first one?
The first is the tag transition probability. This is purely about the flow of the grammar. It asks, okay, I know the last word was a noun. What are the mathematical odds that the next word is a verb?
Ah, so it's looking at the neighborhood. It knows that the cat sat is common, so noun verb is a high probability. But the cat the is really unlikely, so noun determiner would be a low probability path.
Correct. It uses a big rim model for this. It just looks at pairs of tags. It doesn't care what the words are, just the tags. It learns the rhythm of the language.
Okay, so that gives us the skeleton, the structure. But that's not enough, right? You need to know which verb fits a specific word on the page.
Exactly. Which leads to the second probability. Word likelihood. Sometimes it's called emission probability. This one asks, okay, let's assume the tag right now should be verb. How likely is it that the specific string of letters I'm looking at, say kataba, actually is a verb?
So it combines them. How likely is a verb right now times how likely is this word to be a verb?
Yes. It multiplies those two numbers together. And it does this for every possible combination across the entire sentence.
Wait. If it does that for every combination, isn't that just a ridiculous number of calculations? If you have a 10-word sentence and each word could be one of 5 things, the math just explodes.
Yeah.
It sounds like it would take forever.
It would explode if not for the Viterbi algorithm.
I saw that in the paper, the Viterbi algorithm.
Yeah.
Sounds fast. What does it do?
Think of it like a pathfinding tool in a maze. You don't need to map out every single dead end to find the exit. You just need the most efficient route. Viterbi lets the computer discard the low probability paths early on. It prunes the decision tree, so instead of checking billions of possibilities, it zooms in on the single most likely sequence.
Okay, that makes sense. But I see a flaw in this plan, a pretty big one.
Oh.
This is all based on training data, right? You feed the computer a bunch of text to learn the probabilities?
Yes, the paper mentions using about 630,000 words from the Pan-Arabic tree bank.
Okay, so here's the problem. What happens when the computer sees a rare combination? Let's say in all that training data, a noun was never followed by a specific type of adjective. The probability is 0.
Right. In the training data, that sequence never occurred.
And if you have a 0 in a multiplication chain,
The whole thing becomes 0. The system crashes. It thinks the sentence is mathematically impossible.
so how do they fix that? Because rare things happen. People write weird sentences all the time.
This is a classic problem in NLP called data sparsity. The paper addresses it using a technique called smoothing. Specifically, they use methods called Witten-Bell and Nezerny smoothing.
Smoothing. What does that do? Just sort of file down the sharp edges of the math?
It's more like insurance. Imagine you're a bird watcher and you've seen 100 birds and they are all robins. Your raw data says there's a 100% chance the next bird is a robin and a 0% chance it's a crow.
Which is obviously wrong. I just haven't seen a pro yet.
Exactly. Smoothing is the mathematical way of reserving a little bit of that probability for the unseen. It steals a tiny fraction of a percent from the robins and saves it for the mystery birds. So when the computer sees that rare combo, it doesn't give it a 0. It gives it a tiny non-zero number. It keeps the math alive.
That is surprisingly philosophical for a math paper. Always leave room for the unknown.
You have to, or your model breaks the second it steps outside the training room.
Okay, speaking of the unknown, this gets us to what I think is the coolest part of this paper. The real secret sauce. We said there's no dictionary.
Correct.
So, what happens when the computer sees a word it has literally never seen before? These out-of-vocabulary words, or OOVs. If I invent a word right now, splorgification. The computer has nothing. It can't check a list. It's flying totally blind.
This is the make or break moment. In a rule-based system, it would just error out, word not found. But this system gets creative. It stops looking at the word as a whole and starts looking at the shape of the word.
The shape, you mean like the spelling?
Specifically, the prefixes and suffixes. It breaks the unknown word down into character strings. It looks at the first letter, the first 2, the first 3, all the way up to 9 characters. And it does the same for the end of the word.
Right, because even if I don't know what splurgification means, that suppliation at the end tells my brain it's probably a noun.
Precisely. The morphology holds the clue. And this is where they found something really fascinating about Arabic.
The ratio, the alpha weight, I highlighted this.
The alpha weight. The system has to decide, How much should I trust the beginning of the word versus the end of the word? It's mathematically combining these two guesses.
Then you'd think, just split it 50-50. Both ends matter.
That's the intuitive guess. But what they found through experimentation was that the magic ratio for Arabic was 3/5.
Meaning the prefix is weighted slightly more than the suffix.
Yes. The beginning of an Arabic word carries a bit more predictive power.
And the paper contrasts this with English, which is, it's just a perfect illustration of how different languages are under the hood.
It's a stark contrast. The paper notes that for English, if you try the same prefix probability approach, that weight is usually set to 0.
0. As in, the prefix is useless.
Pretty much. Think about it. Take the prefix re. You've got return, a verb, review, noun or a verb, reality, a noun with a different root, or un. You have uncle versus undo. Knowing a word starts with un tells you almost nothing about its grammatical role in English.
But in Arabic,
Because it's a Semitic language built on these root systems and patterns, that initial string of characters is a goldmine. It might indicate tense, or a preposition, or an article.
that's such a cool detail. It shows that while the math is universal, the tuning of that math has to respect the DNA of the language itself.
Absolutely, you can't just copy and paste the settings.
So we have this system that guesses based on grammar flow, probabilities, and word shapes. Let's look at the scoreboard. How well did it actually work?
Well, they tested it on that Penn Arabic tree bank. First, they set up a baseline, just what if we guess the most frequent tag for every single word?
The dumb approach. Just play the odds.
Unigram approach. And that got them 84.3% accuracy.
Which sounds okay, but in a 20-word sentence, you're getting 3 words wrong. That's enough to ruin a translation.
It's not good enough for real-world applications. But when they turned on the full HMM with the smoothing and that clever prefix-suffix analysis, the accuracy shot up to 95.57%.
95.57%. That is incredibly high for a system with no dictionary.
It is. Now, to be fair, the paper does compare this to the old way, those systems with the heavy morphological analyzers.
Right.
And those systems did get a higher score, about 98.1%.
The heavy system is better.
Technically, yes, about 2.5% more accurate.
So why bother with this statistical approach then? If I'm building a translation app, don't I just want the absolute best accuracy? Why take the lower score?
It's a trade-off. That extra 2.5% comes with a massive penalty in speed and memory. The morphological analyzer is slow. It needs to load that huge database. Coverage system is light, it's fast, it's efficient.
It's the difference between driving a tank and a dirt bike. The tank is safer maybe, but the dirt bike gets you there way faster and uses less gas.
That's a great analogy. For real-time applications like, say, voice translation on your phone or analyzing millions of tweets to track trends, you can't afford the tank. You take the 95.5% because it's scalable.
That's a fair point. Good enough and fast often beats perfect and slow in the tech world. But what about that 5% error? Where did the computer get confused?
The error analysis was really revealing. It was rock solid on nouns. The error rate was under 4%.
And noun is a noun. Table, chair, hard to mess up.
But proper nouns names of people and places were a disaster. The error rate was over 9%.
Why?
Because names are the ultimate out-of-vocabulary words. And in Arabic, a name can often look exactly like a regular word.
Right, like the name Kareem actually means generous.
Exactly. So if the computer sees Kareem and it hasn't seen it as a name in its training data, the math just screams adjective. It sees the shape of an adjective. It doesn't know it's a person's name.
It needs context that it just doesn't have. And Arabic doesn't use capitalization to signal a name like English does, right?
Correct. No capital letters, so the challenge is even greater.
And you mentioned adjectives were another weak spot.
Yes. Nearly 20% of all the errors it made were the system confusing an adjective for a noun.
And why is that specific mix-up so common?
Because in Arabic, the structure of an adjective and a noun can be very, very similar. They often share the same morphological shape. So without a dictionary to tell you, no, this specific word is an adjective, the statistics can get blurry.
There was also a note about the tag set. They used a reduced tag set. Can you explain why that matters?
Yeah, this is a bit of a debate in the NLP community. Some systems try to tag every tiny detail case, mood, gender. You can end up with hundreds, even over 1,000 distinct tags.
Like noun, feminine, singular, accusative.
Exactly. This system kept it simple. It used about 17 core tags: noun, verb, proper noun, adjective, and so on.
Keep it simple.
And by simplifying the target, you automatically increase your accuracy. It's just easier to hit a barn door than a bullseye. For many applications, knowing it's a noun is all you really need.
So they prove it works really well for Arabic. But the paper makes an even bigger claim
Hmm.
that this approach is language independent.
And this is the victory lap of the paper. To prove the math wasn't just some fluke for Arabic, they took the exact same code, the same HMM, same logic, and ran it on Farsi and German.
Which are completely different language families. I mean, Farsi uses the Arabic script, but it's Indo-European,
Right.
and German is, well, German.
And the results were shockingly consistent. For Farsi, trained on about 2.5 million words, they hit 95.54%.
That is almost identical to the Arabic score.
And for German, trained on 1 million words, they hit 95.80%.
Wow. So the math just doesn't care if it's a Semitic language or a Germanic one. Probability is probability.
That's the beauty of the stochastic approach. It discovers the structure from the data. It doesn't impose rules on the data. The HMM just finds the pattern, whether it's in German compound words or Arabic morphology.
It's like water filling a container. It just takes the shape of whatever language you pour into it.
That's a great way to put it. It shows that underneath all the surface differences between languages, the statistical properties are often quite similar.
So stepping back for a second, we've geeked out on Viterbi, algorithms, and alpha weights. But what's the big takeaway here? Why should someone listening who might not be building a search engine care about this?
I think the big insight is about a fundamental shift in problem solving. We used to think that for a computer to be smart, it needed to know everything. It needed the encyclopedia, the rule book.
The expert system era, yeah,
Yeah,
where we tried to program every single possibility.
right. But this paper, and really the last decade of AI, proves you can achieve incredibly high fluency just by understanding context and patterns. You don't need definitions, you just need data.
It's the ultimate fake it till you make it. The computer has no idea what love means, but it knows exactly where the word love sits in a sentence and what words usually surround it, and that's enough to translate it.
It's why this technology has accelerated so quickly. We stopped trying to hard-code the world and started building machines that could just learn the shape of the world on their own.
Which leads me to this thought I've been having while reading this, and it's a little unsettling, to be honest.
Go on.
If a computer can essentially fake understanding a language just by looking at the first few letters of a word and the word that came before it, how much of our own reading is just that?
That is a provocative thought.
Seriously, when I skim a news headline, am I really analyzing the deep definitions of every word? Or is my brain just running its own biological HMM? Am I just predicting the next word based on probability?
Well, cognitive science would suggest it's a lot of the latter. We are prediction machines. We don't read every single letter. We sample, we guess. It's why you can still read a sentence if the middle letters of the words are all jumbled up.
So next time you find yourself finishing someone's sentence, just remember, you aren't psychic. You're just calculating the tag transition probability.
And hopefully your personal alpha weight is properly adjusted for the situation.
Exactly. If you keep getting it wrong, maybe you need to check your smoothing parameters. This has been a fascinating look into the mechanics of language. Thanks for guiding us through it.
My pleasure. It's always fun to look under the hood.
And to our listener, thanks for diving deep with us. We'll see you on the next one. Keep listening.